close the doors. Feynman writing, okay? We always have had a great difficulty in understanding the world view that quantum mechanics represents. At least I do. I've entertained myself always by squeezing the difficulty of quantum mechanics into a smaller and smaller place so as to get more and more worried about this particular item. It seems to be almost ridiculous that you can squeeze it to a numerical equation, that one thing is bigger than another, but there you are, it's bigger than any logical argument can produce. This is about the violation of Bell's inequality. It is written in the paper. So he recognizes that it is another mystery, different in nature. Entanglement is even more mysterious than wave particle duality. But finally, as soon as he recognizes that there is something new, he finds a way to use it and he invents quantum computing. And so, whoops. Okay. So, Feynman proposed, and then there were many people like Deutsch and other people, Bennett, Brassard, Ekert, etc., etc. The idea of quantum information is the following. People doing classical computing have a dogma that all computers are equivalent. Of course, some are faster, but the scaling laws are always the same. Okay? But this is if you stay to the same physical properties. If you change the physical properties of the hardware, so if you introduce a possibility to have entanglement in the hardware, then the very way in which conceptually you are going to calculate changes. And so you have the so-called exponential acceleration, etc. So you have quantum computing, which could be much faster than classical computer. We don't know if it works or not, but it's beautiful ideas. Quantum cryptography, which works, which allows you to exchange messages without being spied by security agency of big countries, you know what I'm speaking of. Quantum teleportation and quantum simulation. So just to fly a few things, okay? Just an idea of quantum cryptography, because that's the Ekert scheme that naturally comes from these experiments on Bell's inequality. You have two friends, Alice and Bob. They want to exchange information, and there is an awful eavesdropper who wants to spy. There is a well-known theorem by Shannon, 60 years ago. You know Shannon, the great guy on information, okay? He says, if Alice and Bob have two identical copies of encoding and decoding key, they can use this key to code the message, the other one decodes the message, and the spy cannot do anything. Cannot do anything provided that the message is not longer than the key. Because if the message is longer than the key, the spy will begin to note repetition, make statistics, etc. And well, during World War II it was used, and finally you can break the code if you use a key for a message which is longer than the key. So the problem boils down to how to distribute to Alice and Bob two identical coding and decoding key. They have to be identical, and you want to be sure that the spy has not intercepted it. And the response, the answer is entanglement. Remember that if I send a pair of entangled photons, if I get +1, I get +1. If I get -1, I get -1. And so there are two random series which are absolutely identical. I don't go into details. They can check that there is no spy on the line. From time to time, they turn the polarizer and they make a test of Bell's inequality. If they violate Bell's inequality, they know that there is no spy on the line. Okay. If you ask me question, I will ask you question. QKD at large distance from space is on the agenda, and I understand that China is involved in a collaboration with Zeilinger and Innsbruck to develop such a scheme where you would distribute key for this kind of cryptography from a satellite to distant stations. Okay. Quantum computing, to make a long story short, that the idea that I developed that in a pair of entangled particles, there is more information than the sum of information we could have in one classical bit plus another classical bit. To let you understand, I show you what is the size of the space. When I have two entangled qubits, what is the size of the Hilbert space? Well, let us look at the bases. Plus plus, plus minus, minus plus, minus minus. Size is 4. If I have 3 entangled qubits, the size is 8. If I have 10 entangled qubits, the size is 2 to the 10, that is to say 1,000. So in a single system of 10 qubits, I can encode 1,000 information. In 20 entangled qubits, I can encode 1 million information. Let us stop here. Now, I make an operation, a single operation on these 20 entangled qubits. It means that 1 million data are processed simultaneously. So the key of quantum computation is massive parallelism. This is why smart mathematicians, Peter Shor and other people, have developed algorithms showing that there is an exponential acceleration of quantum calculation due to this massive parallelism. Okay. With this, now last thing, just to flash, there is another way of using quantum computing ideas is to, for instance, if you want to calculate what happens with many electrons in a piece of matter, this is what I do in my lab at the moment, you replace electron with ultra-cold atoms, you replace the potential, the electric potential, the electrostatic potential for the electron, you replace it with an optical potential created by lasers, and you can study the behavior of your cold atom, which mimics the behavior of electron. You are going to tell me what is the advantage. The advantage is I can manipulate the parameter. In a piece of matter, the value of the field is given. The density is given, everything is given. With my atom, I can change the density, I can change the interaction, I can change the size of the potential, etc. So I can explore the behavior of the system. Okay. So, two concepts at the root of what I call a new or second quantum revolution. Entanglement, no need to comment, I have commented for 2 hours. 2 hours? 3 hours? But you should realize this point. This point is very important. One big experimental revolution in the last 4 decades, starting in the 70s, okay, is the fact that physicists have learned to isolate, observe, and control single quantum objects. People as smart as Schrödinger have written in the 50s definitive sentence saying that you will never be able to observe an individual quantum object. You will only observe large ensemble, make statistics, so you can safely use the formalism of density matrix, etc., etc. You will never observe single quantum objects. For the last 40 years, we have learned how to manipulate, you know, this IFM, you manipulate individual atoms. Here, we create single photons. Here, Demel could store single electron and measure single electron, etc., etc. Okay. So these, in my opinion, are the 2 ingredients which are the root of the second quantum revolution. And so, will we have a new technological revolution? I don't know. Will quantum computing and quantum communication system lead to the quantum information society? You know that the first quantum revolution, transistor, laser, and computer integrated circuits, laser again, led to the highway of information. This is the first information society. Will we have a quantum information society? I don't know, but for me, the roadmap is the following. From proof of principle with well-defined elementary microscopic objects such as photon, atom, ion, molecules, to solid-state devices, artifacts, etc., and then we will see what happens. Okay? It's a fascinating issue. We live exciting times. And of course, here are the giants on the shoulders of which we stand. But I was lucky to have a wonderful team when I was doing my experiment in 82. Okay? They were not soldiers, okay? They were kids. Now they are great shots in the quantum world, but they were students, okay? They were undergraduate students at that time. These were technicians, engineers, okay? Now I have a wonderful group, and if you are interested, we have programs of exchange of people between France and Taiwan. And what else should I say? Ah, yes, this, not the. Now, you know, Bell's inequalities are violated every day, 5 days a week in the laboratory classes of Institut. So it's just to tell you that now it's really, well, our students are very good, but anyway, it's really become standard. Okay, with this, I thank you very much.
Thank you very much for your wonderful talk. Actually, you spent much longer time than I expected. Okay. More than 40 sigma.
I warn you. I warn you.
Yeah, you must give us special discount when you buy your book.
Absolutely. I give a discount to my students.
Okay, questions?
Don't be timid. Okay.
I believe Einstein's biggest unhappy about quantum mechanics is still the projection postulate or the wave function collapse. And you emphasize a lot on entanglement. And what's your opinion about this wave function collapse issue?
I think it's a similar issue in the sense that at the end, why are we happy with the image of entanglement that I presented, or with the collapse of the wave function? It's because of non-locality, because of the fact that something seems to happen instantaneously. Okay? So I think that it is that the problem, the unhappiness, it's also my unhappiness. I really like very much all the writings of Einstein. I'm fully convinced by Einstein. So I think I feel a similar kind of unhappiness. And I think it's really similar in nature, because it boils down to the question of non-locality, to the question that if I insist on making an image, then in my image, there is something that goes faster than light. Now, I just a footnote saying this cannot be used to transmit faster than light useful information. This is very important, because the reason when you do, we can make proofs, okay, technical demonstration based on equation, etc., of the fact that we cannot transmit information, useful information, faster than light, even if we accept this idea of instantaneous something, collapse of the wave function, etc., etc. And the proof at the end, if you look, what is the ultimate reason why the proof works? It's because of the fundamental, uncontrollable randomness of quantum mechanics. So in a sense, it also goes to another unhappiness of Einstein when he said God does not play dice. Actually, the reason why non-locality is compatible with relativity is because there is a fundamental randomness in quantum mechanics. This is a little ironical, but it is my personal conclusion. I mean, everybody is free. We all agree on the equations. We all agree that the experiments are correct. So every one of us has to build his own image. Okay. My own conclusion is what I told you. I accept that there is a non-locality. I know that this non-locality cannot be used for crazy things against relativity. And the fundamental reason why it cannot be used is because of the fundamental randomness of quantum mechanics. Another young student here. I mean, oh, there is a young student. Give the question. No, because they are shy. So no, give it to the young student first. Over there. Professor afterward. Young people first. Otherwise they don't dare.
So your point is that since there's a random property of quantum mechanics,
yes.
so the non-locality transports random and non-useful information.
Yes.
So the non-locality is compatible with relativity.
Yes.
Right? So
Yes.
since they are random and
Yes.
it's not useful.
Exactly.
Oh, okay.
Very good. Excellent. Exactly. Exactly. Because, you know, if when the photon arrives here, it has 50% chance to go up and 50% chance to go down, if I could, in this special instance, convince the photon to go up, then Bob on the other side could know what was the orientation of my, well, I have an explanation here. I'm sorry, Chairman. Ask the question I have. So look, how could I transmit information faster than light? Alice decides on an orientation. Immediately something happens here. Can Bob know the orientation of Alice? The answer is the following. If Bob looks at single detection, only looks here, he finds +1, -1, -1, +1. There is no information in that. To get information about the change, what he must look for is to correlation. So actually, what he needs to do is to have somebody looking at the result of the measurement here, taking a normal telephone, no faster than light, and sending the information. And by comparing his result to the result there, then he knows that the orientation has changed. But of course, he did not go faster than light, so it's not useful. So you can say, well, it's not so interesting. Well, first I tell you that in all schemes of quantum information, such as quantum teleportation, you will discover that you are always asked, where is my expert of quantum information? It's here. When you look at all these schemes, you find that there is always a quantum channel which apparently goes faster than light, plus a classical channel which by definition cannot go faster than light. It's the case in quantum teleportation. But there is more. If you say, oh, this is disgusting, we waste 1 hour, it's not interesting, it's trivial. Okay. Now, view the experiment after it's completed. So the experiment is done in the following way. Alice changes the orientation and makes note of all the results. Bob changes the orientation, takes note of all the results. When everything is finished, they take the set of data here, they take the set of data there, put them close together and observe. And when looking, of course it's from an historical point of view, but when looking at it, they have to recognize that it did change instantaneously. Although it could not be used, anyway it happened in the past instantaneously. So it's just to tell you, okay, you cannot use it, but anyway, it's interesting. And I would like to add something for the young student, really important. If something is weird and bizarre, maybe it's a signal that there is something interesting to do with it. Remember Feynman. When Feynman recognized that entanglement was really very weird, immediately he invented something with it. So when something is weird, don't say, oh, okay. No, think more about it. Maybe you are going to invent something nice. Now we have a professor here.
Okay. It looks younger than him.
No discrimination.
You mentioned if the EPR theory fails, then there are two possibilities. One is with non-locality, but there's another option that you still have the locality, but with something else. Could you repeat that?
Yes. Some people, many people, okay, I follow on your question. Yes, to get Bell's inequality, I need two things. I need locality and realism, what I call local reality. That is to say, I need to say that when I have a system which is closed in space-time, okay, a volume of space-time, all the result of the measurement that I will do on this system only depend on the properties which are in that. This is local realism. Now some people say, local realism, there are two hypotheses, locality and the existence of a physical reality. And so when you have two hypotheses, you may ask the question, which one should I reject? So some people say, I keep locality, I reject reality. I rather say, I keep reality, I reject locality. But to be honest, the interesting concept is local realism, because as soon as I reject locality, what does it mean to affect, to attribute a physical reality to this volume if this volume is instantaneously connected to the other one which is here? So you see the notion of reality becomes real vague. And vice versa. People say, oh, I renounce physical reality, but if you renounce physical reality, what does it mean to attribute properties, to say that the result of measurement depends on the property of the system? So my conclusion about this question is the following. Local realism was a beautiful concept issued from the idea of Einstein, which basically are classical ideas, okay, coming back from the 19th century physics. This was a beautiful conceptual idea. Globally, it fails. So we have to abandon, my conclusion, we have to abandon local realism. This for sure. Now, personally, I prefer to think that the wave function has some kind of physical reality and to accept non-locality. But it is, I cannot prove it, okay? What I can prove is you have to abandon local realism. That's the end of what I can prove. My choice after that is to keep a kind of reality, attributing a reality to wave function and abandon locality, but I will not force anybody to adopt this point of view. It's just helpful to me.
Okay, last question.
Professor, how common is the phenomenon of entanglement? Is phenomenon of entanglement a very rare condition, or is it everything is in this world is entangled?
Okay, this is a very interesting question. A priori, everything should be entangled, because as soon as you have an interaction between two objects, they become entangled. So you have an interaction between two objects, they become entangled, this one interacts with another one, so everything should be entangled. And so at the end of the day, the wave function of the universe should be a big, big, big entangled state. Okay. On the other hand, we know that entanglement is extremely fragile versus decoherence. In other words, if I take my two photons, okay, but if now I scramble a little bit the index of refraction or something like that here, then it becomes statistically incoherent. What does it mean? It means that if I have a first pair, I do something, then the second pair will not behave the same way. This is what means decoherence. It means that at the end, you can no longer recognize that you have entanglement, because if you do many measurements, it's not reproducible. And so most of people think that because of decoherence, most of the system become not entangled because of this decoherence. Okay, they decouple from each other because of decoherence. Cosmologists, some cosmologists think that this is not true at all, because when you have a universe, you have a single universe, and you are not going to repeat the experiment many times. There is not a million universes, there is only one. And so for this universe, the global notion of decoherence has no sense. So these are debatable questions. But anyway, for us, people who work in a lab, for the system that we have in our labs, if we want to have entanglement, we have to be extremely careful to decouple the system from all perturbation of the environment. Now, is entanglement important? Yes. First, as I show you, there are all these hope of entangling more and more objects to make a quantum computer. This is going to be very difficult, but it may work. But there are systems which are entangled by construction. It's some system of condensed matter. In matter, and electrons are entangled. And if temperature is enough low that there is not all these spurious phenomena, etc., clearly the problem of this difficult to understand phenomena of condensed matter rely on entanglement. Supraconductivity that was understood 50 years ago and more, the BCA theory, it's a form of entanglement. Many people think that so-called high temperature supraconductors that we don't understand. Remember that we don't have a theory for high temperature conductor. Many people think that it is more related to some kind of entanglement. So entanglement is certainly a phenomenon which is very important, which allows us to understand sophisticated theory, that may allow us to build a quantum computer. On the other hand, Do we have everything entangled? Some people think that it is a case, but I think that it does not have many practical consequences. It's more philosophical consequences than practical consequence when we consider experiment at the scale of our lab. But for cosmologists, it's a real issue. That's all I can tell.
Okay, rather than quantum, I want to add something human. As I think on behalf of the students, the young people here, and also myself, just a curiosity. You started this experiment relatively early.
Yes.
So, but Bell inequality was pretty obscure. So, for instance, what did you know about Clause's work? How did you start? How did you start at a relatively young age?
Okay. Well, the chairman mentioned that I spent some time in Africa teaching. And while I was teaching, I studied seriously quantum mechanics. Because before, my knowledge of quantum mechanics was not so good. So I studied seriously quantum mechanics. And but I studied in a book. By the way, a book you may know, Cohen, Tanuji, etc. It's a good book. When you study in a book, you just study the equations, the mathematics, and the physics, but not about the interpretation, at least not in Cohen Tanuji's book. So I had no prejudice. Because when you study with a professor, I apologize for professors, but when you study, I am a professor, okay? When you study with a professor, the professor will more or less wash your brain in the following sense. When young students hear of quantum things for the first time, for instance, the electron goes simultaneously through the two slits, the students say, "You are a crazy professor," right? Or maybe they are more polite here, but anyway, he thinks, and he asks questions. And after a moment, the professor who wants to do his course say, "Okay, this debate happened between Bohr and Einstein 60 years ago. Bohr explained everything to Einstein, who closed his mouth. So now study quantum mechanics and you will understand later." But later, you are convinced that there is no problem. This is what I call brainwashing. I was lucky that by studying myself, nobody had washed my brain. And then, by chance, somebody, it was not time of internet, okay? Papers were not easy to find, and the paper of Bell was published in an absolutely obscure journal, which disappeared after 4 issues, okay? So somebody gave me a copy of the paper of Bell. I read that paper, and I say, wow, there is a possibility to settle a debate between Bohr and Einstein. Moreover, I fully agreed with the reasoning of Einstein, leading to the conclusion that there should be hidden variables. How come quantum mechanics cannot be completed by hidden variables? Then I started to do my bibliography, and I found that there was no experimental result, apart from the experiment of Clauser, no experimental result to say Bohr is right, Einstein is Bohr. I said, aha, this is interesting. Because immediately I realized that the experiment of Clauser and the other one, but first they were conflicting, but second, they were so different from the ideal scheme discussed by EPR and Bell and these people that there were room for going to a real experiment testing the basis. And the real one from the first day, what I wanted to do was to change the orientation of the polarizer while the photons were in flight. Okay? Because for me, this was a basic conflict between relativity and quantum mechanics. Okay? So now, why was I brave enough to do that? Well, because the French system was a little crazy at that time, but very good. It turned out that I was young, but I had a permanent position as a civil servant. So even if I would fail, even if they would fire me from my position at university, I was sure to earn a salary as a high school teacher or something like that. So, you know, everybody was warning me. Bell himself warned me when I wanted to start. Okay, he asked me, "Have you a position?" I said, "It's small, but I have one." He said, "Okay, let us discuss physics." You know, everybody warned me. You are going to face a lot of opposition of people who think that there is no point in going to that. And the only message that I can give to the students, which is a message that was given to me by a very good experimentalist who is dead now, Val Telegdi. I met him in '76.